Hello everyone, welcome to the ARIES lecture series, lecture 16. I am Bibhuti and today I am going to talk about the sunspots. So it's all about our nearest star, the sun. So before going into the detail of the thing, I just tell you one thing. So how people treat sun in the history. So Douglas Adams once mentioned in his book that far out in the uncharted backwaters of the unfastened end of the western spiral arc of the galaxy lies a small, unregarded yellow sun. So you can see this unregarded word. So people thought that sun is not, there is nothing interesting in the sun. So that's why they used the unregarded word for the sun. And I also believe that somehow if you look at this image, this is the image taken with a normal camera, you don't find anything interesting in the sun. So it's obvious that people thought it's just a ball of fire, nothing else. Even if you go out and take a extremely good telescope and take the image of the sun, you will also not find something interesting in the sun, even with this greater detail. But sun is not always like this. If you look at the suns in some part of time, you will see some dark spots on the solar visible surface. These dark spots visible on the surface are called sunspots. So these sunspots are very important, and why these sunspots are important, I will talk about this today. So just to get a feel of the size of these spots, let's look at this image. In this image, you can see the approximate size of relative size of the Earth in the image. So you can see that the size of the sunspot. So a single sunspot can cover the entire Earth. So how big these sunspots are. So going into the understanding of the sunspots, let's just look back and how we started this journey. So actually, there are some literature who claim that the first discovery of this dark spot was into 330-25 BC. But there is no evidence for that, but only some literature claims about that. And these literature also claims that the Chinese had recorded sunspot observation with naked eye, and they have started the regular observation of sunspot in 23 BC, but we don't have any evidence for that right now. Actual things came in 1607 when Kepler actually he was looking for a Mercury transit and he found these dark spots, and he was so confident about himself that it is not something to do with the sun, it's a Mercury. So he hasn't observed the sun in the next day. So as J. Casanovas written in his article, had he observed the sun the day before or a day after, or had his assistant more competent, then Kepler would be known today as the first modern observer of the sunspot. So he was so confident that he believed that this is not at all something to do with the sun. So the actual today we give credit for the sunspot discovery and first regular observation Galileo. But at the same time, Thomas Harriot, Johannes Fabricius, Christopher Steiner, these three people also observed the sun almost at the same time. So let's look at these images. Thomas Harriot in 1610, in his drawing we can see that there are some dark spots. Similar in Christopher Steiner 1611, you will see that diagram with the beautiful structures on that. And apart you will see the regular observation. So in the animation you can see the Galileo observed the sunspot for almost 2 months and more than that. So this is the image video created using those images. So today we say the Galileo has started the regular observation of the sunspots. But it has taken almost more than 150 years for the astronomers to believe that these sunspots are important for us. So that's why once Christian Horebo written in his diary, even though our observation conclude that changes of sunspot must be periodic. So a precise order of regulation appearance cannot be found in the years in which it was observed. So that is because astronomers have not been making the effort to make observation of the subject of sunspot on regular basis. So they thought that without a doubt, they believed that these observations were not of interest for either astronomy or physics. So you can think that, so it's pretty obvious if you see a dark spot on the sun and there is no direct impact of it on our life, we thought like it's not important for us, and that's why they, even after the discovery of sunspot, people hasn't started the regular observation. But in 1844, uh, Heinrich Sauve, a pharmacist in the German town, amateur astronomer, actually was looking for the planets around the sun and detected a dark spot, and he has taken counted the number of these dark spots in his paper. And after 26 years of observation, when he plotted this number, he found that there is some periodicity, and that periodicity today we know as a solar cycle. So along with solar cycle, we also call it Sauve cycle in the name of Henrik Sauve. But even that time, there is a one guy in Switzerland who thought that there is a these numbers are important, and he developed a formula. He formulated this number that there should be some way to quantify this numbers on the solar surface. So Rudolf Wolf in 1848 given this formula for counting the sunspot number. So that is R, and you can see K 10G plus 9. So K is the correction factor. I will tell you what is correction factor. At that time, Rudolf Wolf has better confidence in himself. So what he had done, along with his colleague, he has given 0.6 to himself and 0.4 to other guys. That's why whatever number I will count, that will have the greater weightage. So that's why he has given introduced the K number. But today the K number is equal to 1. So we have confidence in all the observers. So we just believe that whatever we are counting, that is correct. So these sunspot number, currently also known as international sunspot number, relative sunspot number, or Zurich number. So now let's look at this example. This is a typical example of an image of the sun in a day. So you will see there are 6 groups in this day, and in each group is represented by circle, and the number near the circle represent the number of spot that is inside that circle. So you can clearly see, if you add up all these numbers, you will get 53 and 53, and if there are 6 group, so you will get 113. So in this particular day, the sunspot number is 113. So this is the time when we started quantifying the sunspot number on the regular basis. So now, apart from this number, during the cycle, sunspot also show some other features. Like at the beginning of the cycle, you will see the sunspot at the higher latitude, and as cycle progress, they migrate towards the lower latitude, and this is represented by this diagram, which actually depicting the butterfly like structure, and we call it as a butterfly diagram. So let's look at the original first butterfly diagram. The observation taken by Carrington, Edward Maunder thought that there is something new about this observation, and he asked his wife to just plot the latitude of the sunspot along with time, and he found this butterfly diagram. So this is the first butterfly diagram originally drawn by Edward Maunder's wife Annie Maunder in 1904. But if you look at the recent butterfly diagram, you will see that this butterfly pattern is continuously periodic, and you will see this butterfly, there is a change in butterfly pattern also. Sometime it starts from higher latitude, near 1960 you can see that they start at higher latitude and then migrate towards the lower latitude. So during this talk we will also understand how these things are happening in the sun. So now let's look at this plot. So this is the sunspot number taken from the CILSO, and here I have plotted from 1923 to 2010 the sunspot number. So it's obvious that these numbers and the sunspot on the solar surface will cover some area. So if you calculate the area covered by these sunspot and plot with respect to time, you will see again this periodic behavior. So if you look at all these 3 periodicity simultaneously, you will find that these all things following the exactly same periodicity, that is around 11 years. So we call it as a solar cycle. Now just look at this 400 year of sunspot observation. So now people will they try to go back and reconstruct the sunspot number data. So this is the image you will see in the sunspot observation from the beginning of 17th century till now. So here you will see like the strength of the cycle is not constant, and that make it more important and interesting to work in this area. So if you see the all this, not even a single cycle is exactly equal to the another cycle. So not only in the amplitude, even in the period also, they are all are not same. So, and there is something more interesting around 1650, that near 1650 there are like sunspots are almost disappear from the solar surface. So people first thought that is the limitation of observers. They must have missed, but now we know that they haven't missed it, that it was actually present, and now people are trying to explain this. So we call it as a Maunder minima. So just now look at this. This is again the time versus amplitude plot calculated using this from the simulation by Karak and Mrs. So in this plot, they have plotted almost, you can see that more than 1500 years of observation, and with the different parameters. You can see that even more, with the simulation, we can produce this type of minimum things like you can see here. So there's sometimes sunspot are like almost gone from the solar surface. There is no sunspot on the solar surface for a particular long time. That is important. So people thought that there must be some mechanism in the sun that is somehow they are stopping this formation and then restarting it again after some time. So currently we don't have proper understanding for that. So what is that mechanism? What are those mechanisms that's suddenly stopping the sun to to form the sunspot and again restarting it? So we currently we don't have the understanding of this property of the sun. So just look at this Maunder minima a little bit about the. So there is some in 1887 Gustav has reported that there's some point of time there is no sunspot, and John Eddy was the first one who used this word Maunder minima. And there is some evidence of mini ice age during that era in the Europe. So John A. Eddy he has written in his paper that if solar activity really ceased or sank to near zero level, it places a restrictive boundary condition on physical explanation of the solar cycle and suggests that the workable mechanism for solar activity must be capable of starting and maybe stopping in periods of tens of years. As I already mentioned, we need some mechanism in the sun that can stop and restart the sun to form a lot of sunspot on the surface. So now we got that there's sunspot that has periodic behavior. It's so butterfly diagram, but now we haven't understand what is the nature of these sunspot. So in 1908, George Halley, he pointed out his spectrograph towards the sunspot and found that the spectral line in the sun got splitted and it is polarized also. So just 3 years before 1905, Zeeman effect was discovered. So he found there is a splitting of spectral lines, and from that he concluded that the sunspot are actually the manifestation of magnetic field. That here you can see that here is the slit position of the, and you will see the splitting of the lines here. So here you can see the splitting. So he, from this observation, he concluded that it is the region of concentrated magnetic field. So now if you look at the image of the sun, so this is the image, continuum image taken in the white light band. If you take this image and if you look at the same image in the magnetic field, so if you, this is the image just in the magnetic field instead of white light image. So here in this image you will see the green region where the magnetic fields are strong and it is away from us, and the yellow region where the magnetic fields are in our direction. So you can clearly see that the region where the sunspots are actually the region of concentrated magnetic field from the modern observations. So now, as Robert Layton pointed out, that if the sun did not have a magnetic field, it would be as uninteresting a star as most astronomers believe it to be. So luckily sun has magnetic field and it is interesting. So let's look at the another property of sunspot, that is Hale's polarity law. So if you look at these two images carefully, you will find something interesting. So something changing with cycle. So in this cycle, you will see the yellow in the left side, blue in the right side. In the other hemisphere, opposite. But in the same hemisphere, things changed in the next cycle. So this is called Hale's polarity law. So from one cycle to another cycle, the polarity of sun's magnetic field is changing somehow. So I will come to that point again, how these things are happening in the sun. But here you will see that the polarity. So let's look at this image. This is just a cartoon image of same. So in the cycle N, you will see at the beginning of the cycle, the sunspot with two polarity, and at the same time, you will see in another sphere with opposite polarity. And at the end of the cycle, in the declining phase, you will see this. So, so in the another cycle, you will see that these things has reversed. So polarity has changed. So now, apart with this polarity, you will see something else also in these bipolar region. That is, if you look at this bipolar region, we call it the spot that is near the equator, we call it as a P spot. And the spot that is above, like far from the equator, we call it as a F spot, that following spot and preceding spot. So in this case, you will see that this image is, don't confuse with this image. This is also a magnetogram image of the sun, where the white regions represent the magnetic field in our direction and black represents in the magnetic field in opposite direction. This image is saturated, that's why it is taken as a black and white. And this is another convention to use the magnetogram. So if you join these two, center of these two spots, these two regions, so these regions are actually tilted with respect to equator. And this tilt has some tendency. At the beginning of the cycle, it has different tilt. At the end of cycle, it has different tilt. So, and it also depends on the latitude. So Joyce discovered that the tilt depend on the latitude of the sunspot, and we call it as a Joyce law. So if you look at the sunspot at higher latitude, it has higher tilt. And if you look at the sunspot at lower latitude, it will have a lower tilt. So now, just look at the sun in two different point of time. So this is the minima. So this is the very recent picture, that's day before tomorrow. And if you look at some other time where there are sunspots in the, so still you will not see a lot of interesting thing in the sun. But if you look at the magnetogram image at the same time during the minima, you will again see nothing, small magnetic fields. And if you see during the maxima, a lot of magnetic fields are there. But if you go up and look at this image in the different wavelengths, so this is the image taken from SDO by combining three different wavelengths. So see, during the minima and during the maxima. So in the first image, you have seen it looks like very calm. Still in this image, there is nothing interesting. But if you look at this image, it's too beautiful. There's a lot of things happening, dynamic things are happening in this image. So in the next talk by Ritesh, you will see how these things are going to affect our planet and our atmosphere. So in the next talk, you will see more about these features, how these features are related with us and our Earth. So I will not talk about these features in detail, but I will just now I'm going to answer all these questions I have raised. So now we understand that sunspots are the most prominent manifestation of the large-scale cyclic solar magnetism. So now we must have some questions like why sunspots are cool and in such an environment. If the sun is too hot, how is it possible that some part of the sun is too cool? Then why sunspots show the periodicity of 11 years? Why this solar cycle? And then another question is why we see butterfly diagram? And why Hale's polarity law? Why these polarity is changing in each cycle? To answer all these questions, first question is, are sunspots really cool? Actually, it is not. So if you look at this image in the two part, so in the quiet sun region, the temperature is 6000 Kelvin. and in the sunspot region temperature is 4000 Kelvin. That is the boiling point of platinum, one of the hardest material on the earth. So you can imagine it is 4000 Kelvin. It is not at all cool, but actually it is colder than the quiet sun region. So that's why it's appeared dark. It's actually not dark. So it's a relative term. We call it as a cool because it is a cooler than other part of the sun, that is photosphere or the quiet sun region. So now before going to understand how these sunspots are formed, just let's look at this structure of the sun. So at the center, we have a core where the nuclear fusion is happening and producing a lot of energy. And then we have a radiative zone where energy is transferred via radiation. And then we have a convective zone. The temperature gradient is sufficient enough to start the convection, and we have a transfer of energy from the bottom of convection zone to the photosphere via convection. And then we have the photosphere, chromosphere, and corona as a solar atmosphere. So let's look at the how these sunspots are formed. So to understand that, you have to look at this image. So in this image, I'm saying sometime in the sun, the magnetic field get concentrated in that particular region and form just like a pipe, you can imagine like that. So in this region, you can see at the bottom, these are the region with strong magnetic field. Now, if there is a magnetic field in that, there is a plasma also inside that. So if it is in equilibrium, that means pressure total outside of the tube should be equal to the pressure total inside of the tube. So if that is the condition, if that is not the case, then what will happen? Either tube will expand or get compressed. So in equilibrium, the thermal pressure outside should be thermal pressure, total pressure inside. So outside there is only thermal pressure, only gases are there, no magnetic field in outside this tube, and then inside there is a magnetic field as well as the gas. So thermal pressure and magnetic pressure. And magnetic pressure in CGS unit is given by B square by 8 pi. So since this term is positive, we can say that the P thermal outside should be greater than P thermal inside. That's lead to rho outside should be less than rho inside. So in particular region, if this condition is satisfied, the buoyancy will come into existence. And due to buoyancy, this tube has to rise. And during this rise, so this tube will rise and come out of the photosphere. So at this point, you will see these two spots. So that's why sunspots are bipolar. So suppose this is the direction of magnetic field, you will see the positive polarity here and the negative polarity here. So this is the reason why sunspots are bipolar and how these sunspots are formed. Now, what is so important? Why these regions are cool? So I have given the answer for how these sunspots are formed, but not given the answer for why these regions are cool. So to understand that, let's look at this image. So in this image, you can see that this is the convective cells. So in the presence of magnetic field, convection is not as efficient as in absence of magnetic field. So the region where there is a strong magnetic field, so a magnetic field will suppress the convection in that region. So there will be an inefficient transfer of heat from the bottom of the convection zone to the surface and leads to the lower temperature. So that's why sunspot appear as a dark, and it has because it has lower temperature around 4000 Kelvin to 4500 Kelvin, 35 to 4500 Kelvin, depending on the size of the sunspot. So it is not a fixed temperature of the sunspot also. So you can see that the surface is around 6000 Kelvin, and then in the region it is around, in this picture it is represented by 4500 Kelvin. So now we got the inhibited convection is the reason why sunspots are cool and appear dark. Now the next question is why it is periodic, why we have 11-year cycle. So to understand that, there is a mechanism we call it solar dynamo. We all are familiar with the dynamo term in the school, that like to convert the mechanical energy into electrical energy. So here also in the sun, it is a natural occurring electric generated in the sun, in the interior of the sun, that produce electric current and hence magnetic field. So in the sun, it is called magnetohydrodynamics. It is nothing but just a combination of the Maxwell's equations, that is Ampere's law, Faraday's law, Ohm's law, and along with the law of fluid dynamics. If you combine these two things, you will get a magnetohydrodynamics. So now to understand the solar dynamo, let's start here. So assume that at the beginning of the cycle, during the minima, so that is the magnetic field lines are polar. So we call it as a poloidal field. So it is acting like a bar magnet. Now, so magnetic fields are the function of r and theta. So now, since sun is not rotating as a solid body, it is rotating like a differential rotation. So at equator is rotating faster than the pole. So due to flux bridging. So flux bridging is the condition where plasma in the sun will get embedded with the magnetic field. So if the plasma will move, move the it will also move the magnetic field along with it. So in this case, you will see that at the beginning, the magnetic fields are like this. As the since the pole is equator is rotating faster, the magnetic field get twisted and get stretched in this direction, and it will keep on going. So at some time, these magnetic field lines are pop up from the surface, and you will see the sunspot. So that is the region. So this poloidal field get converted into the toroidal field. So like this, here you can see that the magnetic field getting converted to the toroidal field, but still you will see the poloidal field. So after some time you will see that toroidal field is still there, the poloidal field has reversed. So poloidal field you will get at the end of the cycle, you will get this thing. So now from here to here, it has taken around 11 years. Now I haven't told you about the how this toroidal field is getting converted into the poloidal field. I will tell you about that. So this conversion poloidal to toroidal is due to differential rotation. We call it as a omega effect. So now you can see that from one minima to another minima. This is solar cycle, but the magnetic field is reversed. So it is not actually a complete cycle. So again, you have to do the same thing. So poloidal to toroidal with opposite polarity, and then again poloidal. So now you got the idea why in the toroidal field in the one cycle, in the magnetic bipolar regions has reversed in another cycle, because it is the part of complete magnetic cycle. So that is around 22 years. So actually when we say sunspot or solar cycle, it is actually 11 years, and when we say magnetic cycle, it is around 22 years. So in a one magnetic cycle, you will get two minima and two maxima. So now just look at this image in little bit detail, how these magnetic fields are getting converted. So as I already mentioned, at the beginning of cycle, you will see the poloidal field. Due to differential rotation, it gets stretched and form a toroidal field. Now this toroidal field has two different mechanisms. Actually different mechanism. Here I am only showing two mechanisms. Here you will see this two magnetic field lines will pop up and form sunspot loops, and you will see, and at the end of cycle, this if you like combine all these, if you take the vector sum of all these things, you will get this thing. So actually this effect is called alpha effect, and we call it as this effect as a Babcock-Latent mechanism. I will not go to the detail, but we call it as a alpha effect. So by alpha effect, poloidal field is getting converted into the toroidal field. So let's look at this image. So now when these flux tube are coming out of from the bottom of the convection zone towards the photosphere, since the plasma inside this tube are not allowed to move out of the magnetic field lines, but they are free to move along the field lines. So hence, due to gravity, the plasma inside this tube will fall in this direction here, this side, and another direction here. So now, since sun is rotating, plasma is in motion, experience a Coriolis force, and this Coriolis force is responsible for the tilt of the bipolar regions. That means sunspot groups. So in these two sides, the plasma will experience two opposite force, and one towards the equator and other away from the equator, and it will tilt. So, and it depend on the latitude. That's why this the force is higher at higher latitude. That's why you will see the Joyce law. Means at higher latitude, this Coriolis force is high, and the sunspot will get more tilted at higher latitude. So now look at this image. Here you can see that at some point of the cycle, you will have a two bipolar region with opposite polarity in the two hemisphere. As the cycle progresses, here it is a simulation from the model Sun, Karak and Mrs. in 2018. So here you will see how these things are cancelling out. So here you will see first red, then blue, blue will cancel out, then red, and it will keep on. At the end of the cycle, you will get all poloidal field with the red and blue with opposite polarity. So this is just a pictorial representation of how these tilted bipolar regions are responsible for the production of colloidal field from the toroidal field. So these tilts are very important for this thing. Now just look at this image. This is just a bipolar region. This is just a summary of whatever things I told about the dynamo. So here, this is the toroidal field, and some part of the toroidal field will get pop up from the solar surface and form a bipolar region. And then again, these are bipolar regions are tilted. In another hemisphere, it is just the same but in opposite direction. So that's why we see the bipolar region with opposite polarity in the opposite hemisphere, and these bipolar regions are also tilted. Now that was theory, but if you take the magnetogram image and if you combine and play a movie, you will see this is called the magnetic butterfly diagram. You will see this thing. Now just look at this image and keep on. So you will see how magnetic field configuration is changing on the surface. During the minima, you will see very less, and again it is increasing with opposite polarity. You have to very carefully look at the image that in the each cycle these things are changing. So that is the observed feature. So now just look at this image. This is the longitudinally averaged magnetic field. So you will see that here are some yellow and blue, and earlier here yellow are there. So these blue guys are moving up, and first it's cancelling out all the yellow, and then again it will first during the maxima it will get cancelled out, and then you will see the blue. So this is the migration of these blue guys towards the pole will first cancel out yellow. That is, suppose this yellow is the here yellow is positive, so first this negative guys will cancel out first positive and then will become negative, opposite in opposite polarity. So the same thing is happening in all the cycles. So that's why you will now this is called the alpha effect. So these tilted sunspots and the motion inside the sun, it's carrying the flux from towards the pole and first cancelling out the already polarity, available polarity, and then again producing the opposite polarity magnetic fields. So now if you look at this image, this is the magnetic field of the southern hemisphere and northern hemisphere. You will see at the beginning of the cycle the polar field is maximum here. As the cycle progress at during the maxima, so this polarity reversal happened during the maxima. So during the maxima, the sun's magnetic field is changing. So northern pole is becoming a southern, and southern becoming northern pole. So this thing happening in every cycle during the maxima. But sometimes there is something interesting that at the same time both the pole of the sun is same. Like here you can see in this cycle here at maxima both are in plus, that both are positive. So that is also interesting. Here again you will see sometime. So this is the polarity reversal. So in the sun, in every 11 year, sun's polarity is reversing, and that reversal is not happening at the end of cycle. That is happening exactly near the maxima of the cycle. So now we got the idea like how this polarity reversal is happening. What is the mechanism behind this? These all. So sunspots and sunspot cycle. So now just look at this video. This is just the summary of what dynamo, solar dynamo. You will see a sunspot, lot of sunspots, and then inside the sun this polaroidal field is getting converted from the toroidal field, poloidal to toroidal, and then again you will see large sunspot, and toroidal to poloidal sunspot is dipping down, again it will picks up. So this is the solar dynamo, and along with that you will also see these two colors. So this is the motion of plasma in one direction. This is the magnetic, it is representing the magnetic field, like how these magnetic. So you will see that, right, yellow guys are moving up. So this is here the motion of plasma, we call it as a meridional circulation, but here you will see the that the transportation of the flux. So green guys are going up, and then yellow, and these things are keep up and producing the solar cycle. So that's it, and this is the trailer for the next talk. So how these things are important, and just look at this video. So from the rise of the flux tube from the bottom of the convection zone to the top of the photosphere, and you will see these sunspots are coming out of the photosphere, and then just look at this video. So in the next talk, Ritesh will explain more about these things. So So this is the magnetic fields. It's like a rubber band. It's teared out, and it is not supposed traveling towards us. So then how will it affect? There are some other mechanism also that can happen in the sun, that is sometimes called the filament eruptions. So here in this picture you will see the filament eruption. There are some other eruptions that also carry the charged particles and along with the magnetic fields. So in the first case you have seen that was magnetic field is carrying a lot of energy and traveling towards us. So before coming towards us, it has to pass through the two different planets. So just look at this video and you will see at the end how this thing is affecting us and how it can affect. If it is very strong, it can affect us severely. So now it's coming towards the earth. Now since earth has a magnetic field that is protecting us from this type of solar eruption and charged particles. Now you will see in this animation how these magnetic fields are interacting with the earth magnetic field. So this is the magnetic field of earth in day side and the night side. So when these magnetic fields with opposite, now look at carefully, the magnetic field lines are opposite. So there will be a magnetic reconnection there. I haven't told you about the magnetic reconnection, that is just two magnetic field lines joined together. You can think like that. It is a very energetic phenomenon. It will produce a lot of energy and it will go in the far side of the night side of the earth and it will produce the aurora. So this is the region how these aurora are produced. You will see the charged particles. So if this type of event is very, like, it is carrying a lot of energy, lot of magnetic field, it will come towards us and it can penetrate into the low earth orbit. It can damage our earth and other things, our navigation system, our communication system. So sun is the driving force for the space weather. So in the next talk by Ritesh, you will see the detail about space weather and the sun earth connection. So that's it. Today, this is the image taken during the eclipse from Nainital. And as I have already mentioned, sun is always puzzling for us. And Eugene Parker has once mentioned that sun is the primary puzzle in the universe. So thank you for your attention. Now, if you have any question, please write in the comment box. I will be happy to answer those questions. So there is one question by Shovan Acharya. So in this, he is asking what are the ingredient of sunspot. So actually, I didn't get your what are the ingredient means. So actually, in the primarily sunspot are in the sunspot you will see the magnetic fields. So you already know the plasma is already there. That is convection is already happening. So the only magnetic fields are there. So these magnetic fields are suppressing the convection in that region. So that's why you will see the dark region. Now, since these magnetic fields are very strong, so these can cause other dynamic events. So if I go back and show you some other images. So here, if you see in this image, you will see. So this is the same region. In the sun, in the photosphere, it appears dark, but the same region appears bright in the chromosphere, in the corona. So these magnetic fields are carrying a lot of energy. So that are the main ingredient actually. But if it is not the answer of your question, you can ask me again anytime. So next question is the Srisha, why there are less number of sunspot in higher latitude? So in the higher latitude during the minima, so sunspot appear at higher latitude during the minima. So you will see during the minima not only the less number of sunspot, the size of the sunspots are also small during the minima, because it is the point where poloidal field is getting converted into the toroidal field. So if you look at this image, so here you will see that the order of magnitude of the poloidal field is around 10 Gauss. So actually you will see the 10 Gauss is getting converted into the kilo Gauss. So in sunspot, the magnetic field, strength of magnetic field is around kilo Gauss. So it is the point where it is starting. So 10 Gauss is not exactly just jumping from 10 to 1000. At the beginning of cycle, you will keep it will increasing, so 10 to 100. So that's why at the sunspot, at like only in some regions, sunspot like magnetic fields are strong enough to come out of the solar surface. That's why at the beginning of the cycle, you will see the less sunspot, and only at the higher latitudes, because the buoyancy, there is some dependency on the higher latitude also. And the so main reason is that at the beginning of cycle we have a strength of magnetic field is less at weak magnetic field. So that's why you will see a small number of sunspot, and even you will see the sunspot, it will have a small, you will see the small sunspot, it will have a very less area during the minimum. uh, the sun has Hashika Raj, the sun has sunspot. Do other massive star also have a spot on them? Yes, true. There is some evidence that from the spectroscopy we found that there are some other stars where people has found star spots. We call it as star spot. I don't know much about the star spots, but yes, the answer is yes. Other sun is just a not normal star, so there is no point of thinking that other stars will not have spot. That is our limitation of our technology and the instrument, that we are not able to resolve that spot. So there is nothing special about the sun regarding than other star, but sun is very close to us, and we can study the sun with a lot of detail. So that's why. So your answer of your question is yes. And Harshita Gandhi, can we calculate the lifetime of individual sunspots? Yes, true. We can calculate, but the lifetime of sunspot also depend on the size of the sunspot. So current understanding say that the larger sunspot have larger lifetime. So sometimes sunspot has only lifetime of only few hours, but sometimes it can stay for more than a month. So sometime if it is big enough, you can track for 14 days or 15 days, you will see again the sunspot will disappear from the west limb and it will come again from the east limb. So that is the same sunspot. So it not a fixed number, actually we can calculate it. So we found that from that calculation only, that the lifetime of sunspot depend on the sizes of the sunspot. Why 11, not 20 or 30 years? Extreme good questions. So our current understanding in Dynamo is very limited. We are actually trying to, so this is the not like a general theory of relativity. First we propose the theory, then we try to find the observation. But in solar physics, we have a lot of data, we have a lot of observed phenomena. So we first observe that it is 11 year, then we try to explain the 11 year. So we don't have the answer why 11 years. So there must be, that is due to the this solar differential rotations, that is playing important role for that, but there is some cycle. So right now there is I don't know the answer of why 11 year, because we are trying to explain, and actually it is not exactly 11 year also. So it vary from 8 years to 12 to 13 years. So this 11 year is the average. On average it is 11 years, not exactly 11 years. So it depends on the so many factors, but it is, we haven't seen any cycle with more than 13 years and less than 8 or 8 and 8.5 years. So the answer of your question is like, we are trying to find the answer in the different way. We are not trying why 11 year, we are trying to explain why 11 year. We are trying to find the answer of the, trying to explain why 11 year. We have to want to find the period t equal to 11. So it is just like a reverse problem. And Sachin Sharma, what is the region for magnetic poles exist in the earth? So there is a similar mechanism. It is believed that earth has also dynamo, but that dynamo is a stable dynamo. It is not like sun, it is a stable dynamo. And if you look at the geological history of the earth, you will find that earth's magnetic field has also reversed in the past. So but it is not that frequent, so we are lucky that it is not flipping very rapidly. So again, the mechanism is same. There is something that is happening at the core of the earth, that is, so the dynamo, if you just simple dynamo, definition of dynamo is the mechanism that amplify the magnetic field or sustain the magnetic field in the any object. So in the earth, it is very stable system, and that's why there is no frequent change in the magnetic field. So do we have more suns apart from our sun in our galaxy? I will suggest you to search for just HR diagram, and you will see around the sun there are so many sun-like stars. So you have seen that we always term the mass of the star as a in the term of the mass of the sun. Everything in the with respect to sun. So sun is, I already mentioned, sun is not at all a very special star. So sun is only special for us because it is very close to us and we can look at it very, not with the naked eye, but in more greater details. So that's, it's act like a laboratory for the stellar physics. So solar physics is just like a laboratory for the stellar physics. The stars are too far from us, and that's why you cannot resolve it very like in detail. So sun act like our laboratory. So then another question is whether sunspot group number also clearly show 11-year cycle. Yes, true. So first group number is like sunspot always form in the group, but in the white light image you may not see because you don't have the polarity information. So the definition of group is like when the a group of sunspot, like a set of sunspot that form only from a one flux tube. So we call it as a group. So if that is the definition, all the sunspot magnetic field cannot poke out with only one polarity. So it always comes in a group, and you are right that sunspot group also follow exactly same periodicity. But there is like amplitude difference, you can clearly see that whatever we say in the area is mostly dominated by the larger sunspot. They always form in the group. So they are in the group, but you will also see the single sunspot actually. But in the magnetogram image, you will not see that. So actually it is not, but due to the different strength, and sun is very clever. So it always find a way to puzzle us. So sometimes you will see the black spot, only single black spot, but actually when you look at the magnetogram image, it is actually bipolar regions. So actually it is also a group. So yes, your answer is yes for your sunspot group also follow 11 years periodicity. If there is no other question, then if someone misses today's live lecture, they can find it on ARIES Facebook page as well as the YouTube channel. And please subscribe to our YouTube channel for the update. The link of these sites are also available on ARIES official website. So you can find these things. If you have another question, if you, don't, you can also write in the comment. We'll be happy to answer those questions. That's it. Thank you for your attention. And also please provide your feedback using the link in YouTube channel video, where you can give us the feedback for the quality of lecture. That will help us to improve the lecture in the upcoming. Thank you again.